let me talk about the last part of this class, which is okay. So we're done with centrifugal acceleration, right? So the last thing we want to talk about, as I said, the centrifugal. So this is what we did yesterday, where we talked about the application. I mean, using the centrifugal acceleration concept to solve problems. I mean, we solved this motorcycle thing, but that's not yesterday. I think that's like Monday. And then we did, we talked about the same physics applies to gravitational attraction between the moon and the earth, between the earth and the sun, and even applied to the larger scale for the galaxy, for the universe. Everything has to rotate, otherwise it's gonna collapse, okay? Because we have some ways to be against the gravity. And we did this example yesterday for a turning on the road. Again, there's another application of the this piece of physics we learned about centrifugal acceleration. And then we did this exercise for a roller coaster problem. Again, you shouldn't feel too to be afraid too much when you're going upside down on the roller coaster, because you know that physics tells you you won't fall as far as you're moving pretty fast, okay? And okay, so let me talk about the last thing. I want to talk a little bit astronomy, but I want to talk a little bit about astronomy before we move on to the next chapter, because I think it's a kind of a, I mean, because just for your curiosity, you know, when we were a kid, right, we all looked up to the sky, right, to see wonder what are these things that are shining, you know, and how big is the universe, you know. I think this kind of natural questions, and it's better to, I mean, for us to live, you know, we know a little bit more about the universe that we're living in. So in this class, I'm going to talk about three things, which kind of, again, all of them are related to the stuff we learned, okay? So, I mean, it's amazing that you can learn a lot of astronomy by using Newtonian mechanics, although the full description is given by general relativity, but I think tons of stuff can be understood by using Newton's law. So the first thing I want to talk about is floating in space station, okay? Well, you have seen these kind of videos, I'm sure, right? When you see like people in the space station, like rotating around the Earth, you see those people floating, right, in the air, like there's no gravity. And then the common explanation you heard was there's no gravity there. That's why people are floating, because of space, there's no gravity, okay? Is that really true? It turns out it's not true, okay? Let me show you why. Okay? So we know from gravitational attraction formula, we have this, the full formula is, okay, G m1 m2 over r squared, okay? On the surface of the Earth, we have, I mean, let's put this one as capital ME. This is the Earth, the mass of the Earth. On the surface of the Earth, it becomes this, right? R squared, RE squared m2, okay? Whatever m you have here. Well, this part here is our G, right? So we can call this mg here, right? That's the weight. But when something's not on the surface, you should use the full formula to calculate the gravitational attraction. So what is the, okay, think about it, right? This is the Earth. Well, the space station somewhere here, right? So we know this size, this is the radius of the Earth. But the distance from the space station to the center of the Earth is this radius plus the height. So what is the height of the space, I mean the station, okay? See, what I got here is like, roughly speaking, it is 254 mile, okay? So maybe let me put it in like in kilogram. Okay, 400 kilogram, okay? So we know the height is 400 kilogram, okay? Oh, hold on. Wow, I have a lot of space here, okay? But what about the radius of the Earth? Okay, we know the radius is about 6,000 kilogram. Okay, it's a little larger than that, but let me get a better number here. Radius of the Earth. Okay, in kilogram. Okay, it's like 6,300 or like 6,400. Let's keep that two stick figure. So 6,400. Okay. So what does that tell you? It tells you that in the space station, the person will have a little bit smaller gravitational attraction from the Earth, but not too much. Okay. Say basically, if it's on the Earth, on the ground, you have basically G, ME, and then the mass of the person divided by this number, right? 6,400 times 10 to the third meter square, right? Well, in the space station, you have G, ME, M over this amount, 6,400 plus 400, okay? Times 10 to the third meters square, okay? So basically this is 6,400 squared. This is, times 10 to the third. This is 6,800, okay? So you see that your gravity is smaller, but by a really small factor, okay? So if you want to take this divided by that, you have basically, okay, if I want to use this divided by that, I got basically the ratio of these two forces would be just, so I call it F1, this is F2. So you F2 divided by F1, if the ratio of these two is like 68, okay, 64 divided by 68. So if you calculate it, right, you see that so it's about like 94%. So in the space station, you feel the gravitational force you have is 94% as if you're on the surface. So you get a little bit smaller gravitational attraction, but that's nothing. You know, you should still have a lot of gravity there, okay, from the Earth. So that's really not the reason why everybody's floating in the air, you know. So what is the real reason that everybody's floating in the air? The real reason is, excuse me, the space station is actually rotating around the Earth, okay? And because it's doing rotation, so it needs a centrifugal acceleration. And what force can give you the centrifugal acceleration? It's gonna be this gravitational attraction, right? So you actually have F2 equals to mv squared over RE plus H, okay? You have that combination. So basically, the force you have, instead of pulling you towards the ground of the space station, it provides you the centripetal acceleration so that you can rotate around the Earth. And so the gravitational force on you and gravitational on the space station together, I mean, it's the same thing, that they both provide the centripetal acceleration. So the net effect on you with respect to the space station is nothing. So you don't feel this anymore. You're just floating in the space station because the force already being used to do the centrifugal acceleration. Okay. Well, this might be a little bit harder to understand, but think about another case that you can easily understand. Let's say you're in the elevator, right? Now, if the elevator is doing free fall by itself and you're inside there, right? So what do you feel? You won't feel the force anymore. You feel like you float you're floating inside the elevator because both you and the elevator is going down, doing the free fall. So there's no relative of motion of you to the elevator. So all the gravity has been used to provide you the free fall acceleration. And therefore you're gonna be floating in the elevator that's doing the free fall. Same thing here. If you're in a space station that's rotating around the Earth, again, that force, the gravitational force, has been used to do the centrifugal acceleration. So there's no relative motion of you with respect to the space station. You guys are you're just floating inside the space station. Okay, so that's actually the key why you see everybody in this space station is floating, not because they don't have gravity. The gravity is still there, it's still 94% of gravity, but because everything's floating, I mean everything's rotating. Okay, does that make sense? Okay, now the second thing I want to talk about on astronomy is so-called Kepler's law. Okay, Kepler's laws. Now there's 3 of them, and I'm going to state them, and then I will focus on the third one because that one is what related to us. Okay, so what is the Kepler's 3 laws? Okay, the first law says all the orbits of the planets are elliptical. Okay, so you have elliptical orbits. And amazingly, this is the sun, right? Amazingly, all the ellipses here of the planets are in the same plane, okay? So all the orbits are sitting in the same plane. It doesn't not need to be that like that, but it turns out to be the case. So you have all these elliptical, they're all in the same plane, okay? So the reason they're elliptical is, again, Newton's law. So if you use Newton's gravitational attraction and the Newton's second law, combine them together, you can solve for the trajectory. And turns out elliptical orbits are ellipses are the solution. Okay. Well, circle is one solution, but it's very special. In general, it's ellipses. Okay. So, but we won't do that because that's beyond the scope of this class. Now, the second law says on the ellipse, the Earth go. For example, let's take the Earth, right? For the same amount of time, if you connect the Earth to the sun, it's wipe out the same amount of area. So it's called equal time, equal area law. Okay. And that's a pretty amazing law because it's an ellipse and also the sun is at one focal point of the ellipse. So the Earth will be closer to the sun at one part of the orbit and further away from the sun at some other part. Because this law is basically saying that when the Earth is staying really far away from the sun, it's going to move slower. Well, when the Earth is going closer to the sun, it's moving faster because they have to achieve the same area in the same amount of time. So this part is faster. So the Earth is not really rotating with constant speed. It's actually going like fast, slow, fast, slow, fast, like that, you know, around the on the orbit. Okay, but okay, the one I want to focus on, the third one. Okay, this one says, okay, let me pull out the textbook and we can see it from there. Okay, Kepler's third law. It basically is saying that the size of the orbit, this cube is proportional to the period of the orbit square. Okay, now we can actually got this law by using our centrifugal expansion knowledge. Now for that, for simplicity, let's assume that it is a circular orbit, although in practice it's not. Okay, so if it's a circular orbit, right, for the Earth, now we know F equal to ma, and here you have centrifugal expansion. So you have the gravitational force equals to mass of the Earth times the acceleration, centrifugal acceleration of the Earth on the Earth. So this part here is GME times ME. Okay, so ME times MS. This is the mass of the sun divided by the radius squared. That equals to the mass of the Earth. This is the same mass here. Okay, times the centrifugal acceleration, which is V squared over R. Right. This is the speed of the Earth. Now, what about the period? Okay, you can get the period by considering the speed, right? Because for one circle, the circumference is 2 pi r. So the period is simply equal to the circumference divided by the speed. So that's the period, okay? So that means speed equals to 2 pi r over t, okay? So if you plug this to here, you have GME ms over r squared equals to me. Now v squared, you have this thing squared, so you have 4 pi squared r squared over t squared, and then there's another r here, so it's another r here. Okay. Okay, now you can see me cancel out, right? Well, one of these r's cancel out. Okay, so there's only one r left. Okay, so if you multiply t squared on r on both sides, you have g ms t squared equals to 4 pi squared r cube. Okay, So this is exactly what the third law tells you. The period square is proportional to the size cube, okay, to the size of orbit cube, okay. Or you can write like t squared equals to 4 pi square over GMS R cube, okay. This is just a constant here you have, okay. And by the way, this also provides you a way to measure the mass of the sun, because it's easy to do observations to find out the period of a planet. For example, for the Earth, it is a year. And it's also easy to measure, relatively easy to measure this distance from the Earth to the sun. For example, you can shoot a beam of light, going back and forth, and then measure the time. Anyway, there's all kind of way to measure that. So if you know these and these, you can find out the mass of the sun here, okay? And this is one approach that we can measure the mass, okay? Anyway, so this is another application of what we just learned, okay? Now the third application I want to talk about is called dark matter. You probably heard about this already. People observed this in the last couple of decades, and it turns out the matter we can observe by telescope is only a very small part of the universe. It's about 5% of mass is observable mass, and like roughly 25% is dark matter, which means we cannot see them. And then another 70% is called dark energy, okay? So in some sense, the whole universe is kind of dark because a lot of things are. So how do people discover dark matter? It's very interesting, and it's exactly what we talk about here. So what they can do here is they can observe like some stars rotating around the galaxy. So it's one part of the galaxy, right? It's rotating together with the galaxy. Let's say this is the galaxy here, okay? The whole thing is rotating like this, okay? I mean, let's say go this way, the whole thing. And they can measure the speed of the star, okay? And they can also measure the observable mass of the galaxy, okay? And according to our centripetal acceleration formula, it is the gravitational attraction on the star. So we have a G, mass of the galaxy times the mass of the star, divided by this distance, r squared. Okay, this should be equal to mass of the star times v squared over r, right? This is the force equal to mass times the acceleration. Okay. However, it turns out if you set up this, because we can measure the speed and we can measure the r, and then you can the mass of the star actually cancels out. So from there you can figure out the mass of the galaxy, which is given by v squared times r over g. So that's the mass of the galaxy figured out by using this simple combination, okay? You can plug in v and r and g. It turns out the mass measured this way is way bigger than the mass of the observable mass you have in the galaxy. So mg, this mass here is way larger than observable mass. And this is what people start to realize. There is some hidden mass there, dark matter. They cannot be seen, but they do have some effect here, like in terms of gravitational attraction. They are there, but we cannot see them. And so far, nobody knows what dark matter is. It's not, but people know it is not what we've known, all the elementary particles on the Earth. So something totally different, okay? And what it is, nobody knows. It's a very big mystery and a very interesting question to think about, And as I said, about 20% or 25% of the mass in the universe is dark matter, okay? I think one thing is pretty amazing for you to see is you can actually understand the dark matter idea by simply using this piece of physics we just learned in this chapter, okay? And this goes all the way to the frontier of the astrophysics study research, like right now, okay? First of all, it provides you some application of the physics we just learned, and like all the three cases are basically this centripetal acceleration here. Well, the first we have here is gravitational attraction. but the idea is the same, right? This attraction provide you the central actuation, you know, and that give us some conditions, so we can use that to study. And it's as simple as that, you know, to see something like dark matter. Okay.